Okay, so we're going to start off our unit on work and energy and power for AP Physics 1 with a brief discussion of different types of energy. So here's my suggestion to you. If you ever get a physics professor in college or some other person that claims to know everything, there we go, and they tell you they have a definition for energy, I can tell you right away, they're full of it. What energy actually is pretty hard to define. I've heard people talk about energy and work and say, like, you know, energy is the ability to do work, and then work is the change in energy or the transfer of energy, and you're like, well, wait a second, it's circular definition, and you would be right. So don't think too hard about what energy is. Don't worry about that. But know this, that energy makes a lot of problems in physics a heck of a lot easier. And we'll see a bunch of examples for that as we go through. So my advice to you, you get onto an AP exam and you're not sure what topic to use for a problem, first place you look is energy. Look at energy first, because that's going to make the problem. If you can solve it that way, it's going to be a heck of a lot easier than forces, and much easier than, say, kinematics. Kinematics is the first thing we usually talk about in this class, and it's therefore the thing that everybody wants to apply to everything. Really, kinematics won't show up that much, not nearly as much as understanding energy. As far as different types of energy are concerned, think of anything that can hurt you, and you're really looking at energy. This is my bizarre way of looking at it. If somebody is walking along the street and they're walking close to the curb, no big deal. But if someone's walking along a hiking trail and there's a cliff of 1,000 feet drop on one side, and they're walking this close to the edge of the cliff, there's more concern. If that was your child, you would probably express some interest in them not being that close to the edge. But if they're that close to a curb, yeah, whatever. They're going to fall half a foot, no big deal. So there is a form of energy. Right? You know instinctively that being next to the cliff is worse, because in that case we would say you have more gravitational potential energy. If you are standing in a park and a small child is running at you, runs by you, for example, you're not particularly worried about that. If they run into you, who cares, whatever. But if you ever have the misfortune of, say, having a flat tire on a major interstate, and you're standing there on the shoulder of the road, you're a large truck go by you at like 70 miles an hour, that is really terrifying, to be honest with you. I hope you never have to go through that, but it is very scary. And once again, that instinctive fear of that is an expression, or that's your gut feeling on energy. The truck has what we call kinetic energy. It's bigger and it's moving faster. There's more kinetic energy than the small child running. If somebody walked into the room with a hand grenade, this would be a problem, right? Why? Because we instinctively know, or at least from watching enough movies, that hand grenades contain a form of energy. They contain chemical potential energy. That's one other type of energy. If you want to know more about chemical bonds and chemicals, that's the chemistry teacher's problem, not mine. But the food you eat is less dangerous in the short term, but it also has chemical potential energy. If I go and take a paper clip and I go walking towards an outlet to stick it in the outlet, if a little kid were to do that, you would scream at them, tell them, don't do that, that's bad. That's because there's something inherently dangerous about that outlet, and that is it has electrical energy. So there's all kinds of types of energy. Thermal energy, I remember very well, very hot burner on the stove, and I couldn't see, it wasn't red anymore, so as a small child I asked my mom, is it hot? She said, yes, don't touch it. And of course, I did. And I found out about thermal energy, and now I know when things are hot, they're dangerous. I learned things. So, all kinds of different forms of energy. We're going to learn about many of them, some of them more specifically than others. Some will be very specific, equations and everything. Others, like thermal energy right now, it's a physics topic. It's not in the scope of AP Physics 1. We'll get a rough idea of what's going on with it. So, some things about energy to keep in mind. It is a scalar quantity. And what that means, when we talk about something being a scalar quantity, is that direction doesn't matter. Hallelujah. Because right now you've spent a bunch of time probably doing kinematics and forces where everything is a vector, particularly with forces, all kinds of components and you can't just add two vectors, right? You've got to break them into components and then add their x components and then add their y components and then recombine them using Pythagorean theorem. Right? Adding two vectors is a process. When things are scalar quantities, that is non-vector quantities, that means direction isn't important. All it has is a magnitude. In the case of, the only thing I will warn you is that the quantity work does not have a direction per se, but it can actually be positive or negative. And that is more in relation to, in rough terms, did energy go into the object or did it come out of the object? Did the transfer of energy leave or enter into the object in question? That's kind of the way you want to look at work. But it's in general, in fact, not in general, it is, all energy and work are scalar quantities. So, if something is moving in this direction, has a certain mass and a certain velocity, it will have a kinetic energy. If it is moving in this direction, has the same mass and a different velocity because of the direction, but the same speed, we'll say, guess what? It will have the same kinetic energy. The fact that it is moving in another direction means absolutely nothing. So it makes working with energy much easier because we don't have to worry about all that vector stuff. And as you'll learn as you go through, hallelujah, that's going to make things a lot easier for us. Anytime we deal with work or energy, the units we're going to use, so there's a little bit of a preview. We're going to discover in a moment that work is force applied on an object times its displacement. So interestingly enough, both of these are vectors. And there's a cosine that goes in there, but we'll worry about that later. Both of these are vectors, but it turns out work is not itself a vector, as we'll see. But the reason I bring this up is we know force to be newtons, and we know displacement to be meters. And by the way, if you don't remember, a newton is a kilogram meter per second squared. And when we multiply that by another meter, we get the kilogram meter squared over second squared. But we don't have to call it that every time we refer to it. If we have a certain amount of energy and we use these units, which, by the way, we will always use in physics, except maybe in thermodynamics where there's some weird stuff, but even there we'll use this unit. The unit's name of that set of units, kilogram meter squared over second squared, is a joule, named after somebody with that last name who I should probably know better, but it doesn't really matter because he's dead. So what's he going to do? Capital J. So if you have a measure of 50 joules, that's an amount of energy. Actually, it's not all that much energy. 1 joule is really not a large amount of energy. So keep that in mind as well. You may get very large numbers. A moving truck has quite a number of joules. It's not going to be 50. So keep that in mind as we go. So there's a little bit of an overview here. The units for work and energy, what different types of it are, and actually, let's do this too, I think. Let's go conservation of energy. We're going to add this to this video. So conservation of energy, this is really in very general terms. Energy cannot be created or destroyed. It can only go from one place to another. So I'll give you an example as best I can. So, for example, the sunlight that hits us is energy. We know this, right? So that sunlight comes down from the sun, and let's say, for example, this is my example for conservation of energy. So you have sunlight, which is green today because, well, where's the yellow? Whatever. So that sunlight comes down and lands in the water. Okay, I can make water. Hits water, and say hits and is absorbed by plankton. Those tiny, they would call them photoplankton. I think photoplankton? Yes, I think it's photoplankton, which are the little creatures in the water, little plant-like material that absorb it, and through that process that I'm sure you've all learned about, photosynthesis, convert the sun's energy, that electromagnetic wave, that's what we call it, the sun's energy into stored chemical potential energy. So we have electromagnetic waves or light energy. And by the way, it all started as fusion in the center of the sun. And then it transferred to electromagnetic waves. That energy was absorbed by the plankton and turned into chemical potential energy. And those guys were eaten by little plankton that are actually animals. So they're tiny little creatures, not tiny little plants. Here's one of them right now. Looks like Pac-Man. Don't worry about it. There it is. So they eat the photoplankton and also still absorb that chemical potential energy into themselves. So it's still chemical potential energy. It's locked up in some chemical bonds. Did I mention all of this was taking place millions and millions and millions of years ago? Because then these guys die. See, and then they die and they floated to the bottom of the ocean. This is not, by the way, I'm not making this up. This really happened. Float to the bottom of the ocean. Over millions and millions of years, they get covered with sediments. And, they start at water, they cover it, and they're compressed and heated, and they sit there for millions of years. Rotten, nasty. So you imagine, if you happen to, stumble upon some of this rotten, ugly, nasty stuff, millions of years later, it wouldn't look all that great. It might look like, I don't know, crude oil. Yes, as a matter of fact, it would be crude oil, the stuff that they're pumping out of the ground. So it's interesting, a lot of places where they get crude oil used to be places where there were the oceans, right, at the bottom of an ocean. Texas used to be an inland sea. So it's really flat out there. So you have, at the bottom, you have all that chemical potential energy that has been stored for us since the time of the dinosaurs. Since T-Rex was walking around, and it was some sunny day when T-Rex was on land walking around. He's over here, it's T-Rex. I'm not going to attempt to draw T-Rex. You get the idea. Big legs, little arms, lots of teeth. All right, so there's T-Rex. And it's at that time that the sun's energy was stored for us. Millions of years. We pull it out of the ground. We separate it into its various parts, one of which is gasoline. You put it into your car. Your car burns it, turns it temporarily into, or in some cases permanently, into thermal energy. It heats the gases around it. Those gases expand, and that thermal energy is used to make the kinetic energy of your car. And you drove to school today, or were driven in a bus. If you walked, you get the idea. So you used the sunlight from millions of years ago to get to William Penn. That's what you used it for, to get here. That's a great choice. It's a great choice. So you get here, and now when you had kinetic energy coming to work, you get to work, school here, you park your car. Where did that kinetic energy go? See, this is at the heart of conservation of energy. See, the idea is, energy just can't disappear. You can't just say, well, we had energy, now all that energy is gone. You'll hear me even say that sometimes. What really is happening is it's never gone. There's one place that energy will end up going to eventually. And once it does, it's really hard to get it back. In fact, ultimately, you'll never get it all back. And that is thermal energy. The brakes of your car get really hot when you stop. There's a lot of friction between the brake pads and your wheels, and your car, and all that kinetic energy, pardon me, is turned into thermal energy. And your brake pads are hot, and then gradually that heat goes out into the atmosphere, and the molecules of the universe are moving that much more rapidly, which is basically all thermal energy is. But the energy that fell on that sunny day millions of years ago, it never went away and never will. It'll always be, and now it's in the universe in the form of thermal energy. So we can get it to change forms. This is what example of that. And by the way, you could also, if you didn't want to drive to work, maybe you burn it at the local power plant, and where it was turned into, through thermal energy again, into electrical energy, and you use it to plug it in your car. So either way, the energy would, if we use what they call fossil fuels, does that name now make more sense to you when they say fossil fuels? Because it's from the time of the dinosaurs? It's a long time ago. That's why they call them fossil fuels. Coal being another one. Coal, I think, tends to be plants, like swamps, like that kind of thing. And I believe plankton are the cause of, believe it or not, of where we get oil from. And by the way, that's a lot of oil, right? That's a lot of dead things from millions of years ago. So this is an example that conservation of energy is a very important concept for all sciences, to be honest with you, but physics in particular, this unit obviously in particular. So ultimately, energy is always conserved. If you catch me saying, oh, the energy's lost, what I really mean is that the energy is now in the form of thermal energy and is of less use or no use to us at that point. What I may, better statement would be there is no more what we call mechanical energy, as we'll find out later. But for now, just keep in mind that conservation of energy is an important concept, and it is an overarching one.